Welcome to The Explainer. Today, we're diving into a phenomenon that literally connects the visible physical world right in front of us to the deepest, most complex theories in all of physics. We're talking about a journey that kicks off with simple heat and goes all the way to the birth of the universe itself. So let's dive right in. Why do objects universally change color as their temperature goes up? We've all seen it, right? You flip on a space heater or peer into a toaster, and as that metal heats up, it gets this very distinct red glow. But then you look up at the night sky and you see stars burning with this piercing bluish-white intensity. So what's the hidden rule here? What actually connects the exact temperature of an object to the light it pumps out?
To demystify all this, we'll follow a quick roadmap. First, the glow of heat. Second, what is a black body? Third, the physics of color. And finally, black bodies in space.
Section 1. The glow of heat. Thermal radiation.
Okay, let's start with a fundamental truth. Absolutely all normal matter with a temperature above absolute zero emits thermal electromagnetic radiation. You're actually emitting it right now. To a snake, you're basically a walking glowing beacon. But at room temperature, around 23 degrees Celsius, that radiation is completely in the infrared spectrum. So it's totally invisible to the human eye. Sure, thermal cameras or certain reptiles can pick it up easily, but for us, the energy is definitely there, it's just operating at a wavelength we can't naturally perceive.
Now, things get really interesting when we turn up the heat. For centuries, blacksmiths have judged a metal's exact temperature just by looking at its color. Once an object passes what's called the Draper point, which sits around 525 degrees Celsius, that invisible infrared radiation starts creeping into the visible spectrum. It starts off as this ghostly faint red glow at 480 degrees, but push that temperature up to 930 degrees and boom, it shifts to a bright orange. Keep pushing past 1400 degrees, it becomes this dazzling bluish white. The color is literally telling us the temperature.
Section 2. What is a black body? An idealized concept.
So this brings us to a crucial definition, and it's really the foundation of everything we're talking about today. Blackbody radiation is the thermal electromagnetic radiation emitted by an idealized, perfectly opaque and non-reflecting object, a so-called blackbody, that is in thermodynamic equilibrium with its surroundings. Now the key here is that its spectrum depends solely on the body's temperature. That one factor completely dictates the characteristic glow of objects like heated metal, glowing stars, and, even those toaster coils we talked about earlier. By absorbing absolutely all radiation and reflecting zero, this idealized object gives us a perfect baseline.
But here's the catch. A true, perfect black body doesn't actually exist in nature. Even highly absorbent materials like graphite reflect a tiny, tiny fraction of light. So physicists have to approximate it in the lab using something called a hole-ROM. Basically, it's a heated, opaque cavity with a tiny hole. Any light that enters that hole just bounces around the inner walls until it's completely absorbed. Because of this, the radiation that eventually manages to escape from that little hole is a perfect, continuous spectrum of cavity radiation. And amazingly, it's completely independent of whatever material the walls are actually made of.
Now, the central irony here is just fascinating. A perfectly black body is a theoretical ghost. It has an emissivity of exactly 1, which means it perfectly absorbs and emits all energy. Real objects, on the other hand, have an emissivity of less than 1, since they reflect or transmit some light. We actually call these gray bodies. And yet, this purely theoretical ideal is the ultimate skeleton key for us. We absolutely need the math of the perfect black body to accurately measure and understand all the real, imperfect, glowing objects out there in our universe.
Section 3. The physics of color. Governing laws.
So when physicists really dug into black bodies at the end of the 19th century, they unlocked 3 core mathematical laws. Together, Planck's law, Wien's displacement law, and the Stefan-Boltzmann law completely explain the exact relationship between an object's heat and the light it projects.
Don't worry, we aren't getting bogged down in heavy algebra today. Instead, let's just look closely at 2 of these laws to figure out our toaster and our star.
First up is Wien's displacement law. This rule simply tells us that as an object gets hotter, its maximum emission peaks at shorter and shorter wavelengths. This right here explicitly proves why a cooler toaster coil peaks at a dull, lower energy red, while an incredibly hot star peaks at a much higher energy white or blue. The temperature is literally pushing the peak of the light across the visible spectrum.
Next is the Stefan-Boltzmann law, and this one is all about the sheer amount of energy being blasted out. It says the total radiant heat power emitted is proportional to the 4th power of the absolute temperature. To give you a sense of scale for what the 4th power really means, think about a standard incandescent light bulb filament.
It sits at roughly 3,000 Kelvin, which is about 10 times hotter than room temperature. Well, because of that fourth power rule, that tiny filament radiates 10,000 times more energy per unit area than a room temperature object. Crazy, right?
But mapping this continuous spectrum wasn't easy. It actually posed a massive problem for classical physics, leading to what was dramatically called the ultraviolet catastrophe. To solve the math in 1901, physicist Max Planck was forced to make a pretty radical assumption. He proposed that electromagnetic energy wasn't a continuous wave, but rather that it was quantized into discrete little packets. So by just trying to explain the simple glow of a black body cavity, Planck accidentally triggered the entire field of quantum physics.
Section 4. Black bodies in space, measuring the cosmos.
5,800. That is the effective temperature of our sun in Kelvin. And you know what's cool? Because we understand black body radiation, we don't need to send the giant thermometer to the sun. We literally just look at its light. Our sun is a remarkably good approximation of a black body, peaking right in the central yellow-green part of the visible spectrum. By analyzing that spectrum, Wien's law hands us the temperature directly.
But shockingly, the most perfect black body spectrum we have ever observed in nature doesn't come from a star at all. It comes from the empty space between them. The cosmic microwave background radiation, which is the literal afterglow of the Big Bang, rests at a freezing 2.7255 Kelvin. It is an almost flawless blackbody spectrum, acting as a perfect snapshot of the universe when it first cooled enough to let light travel freely.
So I want to leave you with this provocative thought today. Just think about the incredible leap in human understanding here. A simple, industrial quest to understand why a heated piece of metal in a blacksmith's forge turns red fundamentally unlocked the two greatest extremes of science. It gave us the subatomic, quantum world on one hand, and the ability to map the thermal history of the entire universe on the other. All of that just from looking closely at the glow of heat. Pretty wild, right?